Welcome to Ask and Learn.
In this problem, we have a mass spring system which is oscillating on a frictionless track, and we're told that the velocity of the spring will vary linearly with its displacement. And we're asked to find first the total kinetic energy of the system, and second, the period of oscillation of the system. So how we'll do this problem, for the first part, finding the total kinetic energy, the total kinetic energy will be the sum of the kinetic energy of the block, the mass capital M, which is just simply 1/2 capital M V squared, plus the kinetic energy of the spring. And it will be a little more complicated to find the K of the spring. So what we'll do is we'll break it into a segment. So we'll look at the segment dx, and we'll find the kinetic energy for that segment, and then add up all those segments, so integrating over the whole spring to find the kinetic energy of the spring. And then we'll have our total energy. And for part B, to find the period of oscillation, we'll need to recognize when potential energy and kinetic energy are maximums, and use conservation of total energy to relate the two of those to each other. And then we'll look at our position and velocity expressions for a simple harmonic oscillator. We'll be able to get our angular frequency and our period from those relations. Okay, so part A, looking at our spring. So we're given expressions for velocity, Vx, we can say equals x over L times V, where L is the maximum displacement of our spring. And we're given dm. So if we took in a segment of mass dm, we could say that was equal to small m, total mass of the spring divided by the displacement L times dx. So we can say our k dx, so kinetic energy for this segment dx, would be equal to 1/2 mv squared. So our mass of that segment is dm, and our velocity is vx, right? And so then we'll rewrite that with our given expressions for dm and vx. So 1/2 m over L dx times x squared, times x squared over L squared V squared. And that will become mv squared over 2L cubed times an x squared dx. So total kinetic energy of our spring will be integrating from length L to 0 this mv squared over 2L cubed and x squared dx. And so that will give us an mv squared over 2L cubed, and the result of our integrand will be x cubed over 3 from an L to a 0, and that works out to little m v squared over 6. And k of our block, just simply 1/2 capital M v squared. So our k total is equal to the kinetic energy of the spring plus k of the block. And so you see we'll have a v squared in common there. And we can write that as 1/2 m plus capital M plus little m over 3 times v squared. All right, so that will be our total kinetic energy for part A. And then part B, so we want to find the period of oscillation. So to get there, first we want to think about our what we know for energy. So we can say our total energy is going to be a constant, and it's going to be equal to the potential energy U plus the potential energy K. And we can say a few things about Umax and Kmax. So when our potential energy is a maximum, our kinetic energy will be 0. And at our maximum kinetic energy, our potential energy will be equal to 0. And from there, we can say that our Umax and Kmax will be equal to each other, and they'll be equal to the value for total energy. Okay, so we know that the maximum potential energy will be at the maximum displacement, which is that L. So we can say U max equal to, so what our potential energy of a spring, 1/2 kx squared. So it'll be equal to 1/2 kl squared. And our maximum kinetic energy we can express as our 1/2 m plus capital M plus small m over 3 v max squared, since in part A we found the total kinetic energy of the spring to be equal to that. So the maximum kinetic energy will just be when this velocity is a maximum. And so we're going to say that Umax is equal to Kmax. So we've got 1/2 KL squared is equal to 1/2 m plus m over 3 Vmax squared. Right, so 1/2 KL squared equals to 1/2 m plus m over 3 Vmax squared. And from there we get the value for Vmax equal to square root of K, so our spring constant K over big M plus little m over 3, and all that times an L. Okay, so we've got an expression for our maximum velocity in terms of K, M, big M, small m, and L. Now, what else do we know about our position and velocity? Well, this is a simple harmonic oscillator. So we can write expressions for position and velocity. And the general expression would be x is equal to a cosine omega t, omega being, so a is our amplitude, maximum amplitude, omega our angular frequency, v of t being equal to dx dt, which will be minus a omega sine omega t. And we know that our x max is equal to L, right? And we also know that if we look at this x of t expression, it's going to be a maximum when cosine omega t is equal to 1. So that's equal to a. Right? So we get that this a amplitude is equal to L. And then for our Vmax, so looking at this expression for V of t, that's going to be a maximum when sine omega t is equal to 1. So our Vmax, actually when sine omega t is equal to -1. So our Vmax is going to be equal to a omega. And now this is where this will come in, where we've just found that expression for Vmax in terms of K, big M, little m, and L. And so we can say, since we just found that A is equal to L, so Vmax equals to L omega. Okay, so now we can relate these two expressions for Vmax. So we have an L omega equals to square root of K over m plus m over 3 times L, and cancel an L, and we've got an expression for our angular frequency omega. Omega equals to square root k over big M plus little m over 3. And the last step, change that frequency into a period. So we can say period t equals to 2 pi over omega. And so we get t equals to 2 pi times square root of capital M plus little m over 3 over k. And so that will be our answer in part B for the period of oscillation of our system.